So, the second main thing second main topic is introduction to nonlinear structures. So that the physics-oriented people know where I'm going. So the direction of our aim in a few lectures after this is classical mechanics. From a modern viewpoint. And after that, geometric quantization of the classical systems. These are big words. As you know, the title of the course is Foundations of Mathematical Physics, so I will emphasize in all this discussion the foundations. So, the first nonlinear notion we will discuss and have discussed last week. Thank you, Anna, if she's still here. Are you here? Yeah, thank you for lecturing. The notion of manifold. It's not a new notion. It's a very important notion. Anna discussed in detail. Just keep in mind the following picture. That you have some set which you're trying to understand M, and you have regions on this set, say this one is called U alpha, maybe this one is called U beta, and these regions are equivalent to regions, say V alpha in Rn. So on this abstract set, they are abstract regions, but they're equivalent by some things we call coordinates. Coordinates. You do it all the time in physics, and I guarantee you haven't thought carefully enough about it. And I say the same as mathematicians. So we discussed linear frames, we discussed linear coordinates, and that's because we were discussing geometry on linear spaces. Linear coordinates preserve the linear structure. If you have a linear mapping written in one coordinate, it's... If you have a linear mapping written in one coordinate, it's some matrix. You can write it in some other coordinates, another matrix. But in both cases, it's a linear mapping. It's preserved by the coordinates. Here, these coordinates that you have here, x alpha, and in case, say, this one here, the coordinate you get here is x beta. The way to think about this is they are smoothly compatible. Remember, If you have a linear mapping and you write it in one coordinate, it's a matrix. You write it in another coordinate, it's a matrix. But it's still a linear map. It doesn't care what coordinate you use. There might be some good coordinates, some bad coordinates, some complicated, right? You have to agree with me, right? Here, the notion is not linear. The notion is C infinity. And smooth means C infinity. That means infinitely often continuously differentiable. Okay? Or in some circles, as differentiable as you need in some problem. Okay? It means if you have a function in one coordinate, which is C infinity, and you write it in the other coordinate, it's also C infinity. That means change of coordinates is C infinity. Now how stupid can this be? Okay? What did I say? Smoothly compatible. You say that at night to your girlfriend. Hey mama, we're smoothly compatible. Yeah. Smoothly compatible. It means you're interested in smooth functions, and if you write the smooth function in one coordinate, it's going to look one way. You write it in the other coordinate, it's going to look another way, but it's going to be smooth in both coordinates. Okay. One of the arts of calculations in physics, as you know, is find good coordinates when you can compute. Right? So that will be the case here also. So that's the notion of a manifold. And now, let me tell you one of the most important manifolds. After all of this discussion, one of the most important manifolds is the following example. M, just a small example, is the interval from -1 to 1 in the real numbers. It's a manifold. Well, I have to give you a coordinate system. Okay. The real numbers have a canonical, as a field, more or less a canonical coordinate, right? Right? X. We forget, well, the value of x at the identity is 1, the number 1. We could take 2x and it would have the value of 2 at the identity. So that is pretty stupid. We take just x. And in some sense, that's then canonical, right? Because we have the way of choosing it is the canonical linear coordinate on the field of real numbers. So I use this coordinate. It happens to be a global coordinate. Okay, so it happens to be a global coordinate. So x, which is the identity, is a global coordinate. You don't, it's defined everywhere. You don't, well, it's great, you love it. Right. You don't love it because all of mathematics is nonlinear. And this is a linear coordinate. You have to agree, it's a linear coordinate. You have to agree all of mathematics is nonlinear. Now let me look at some nonlinear stuff. Namely, a function, well, which is C infinity. Let's call this thing, to make some smart. Oh no, it's called n, which is C infinity on n. A smooth function on n. Okay. As differentiable as you like. Anything you like, okay? 2 times 29. Let's say every derivative. Okay. For example, assume for fun that f of 0 equals 0. I talked to a student today. Mathematics, you will see in this lecture, I do everything from the point of view of phenomenology. I do not care about forward thinking. I care about backward thinking, starting with something interesting and seeing what happens. Right? At the end, then we write down something, right? But not at the beginning. Okay. Well, I want to understand this function. And you all know, in some neighborhood, of 0, this function is f of x is x times some other function. It divides it. Do you know that? You love it because you know that from linear mathematics. If you have something that vanishes, then x divides it. If you have a polynomial that vanishes at the point a, then x minus a divides the polynomial. Here a is 0, right? Right? X divides the function. This is a theorem. Do you know this theorem? You better know this theorem. This is the first fundamental theorem in calculus of one variable. This is the first fundamental theorem in calculus of one variable. Okay. Suppose this function vanishes. Let's have some fun. It could happen. Right? It could happen. Then you're not stupid. You say, well, what I'm going to do is that I'm going to do the thing again. So I'll do it again. And we write f is equal to x squared times f2. Right? I did it again to f1, right? If f1 vanishes, I divide again. Right? Let's have some more fun. Suppose f2 vanishes. Then, well, you're getting tired of me. Right? Suppose, oh, let's have some really big fun. Suppose all the derivatives vanish. That's an interesting thing. You know that, you know there are functions like that, right? You know functions like this. You know a good example? What's the first example of, if I give you an oral examination on calculus or something, what's the first example? Do you know one?
Just x to the n. That's a comp.
Well, let this guy talk. Come on. By the way, I saw these videos and I'm going to repeat everything that comes from the audience. So if you say something stupid, I'm going to repeat.
So you mean that all the derivatives are
Zero.
Zero.
At the origin.
Just f of 0.
At one point. F prime, F double prime, F3, but only at 0.
Just constant function.
Wrong. So he claims if a function vanishes at origin, first derivative vanished, second derivative vanished, third derivative vanished. Yeah, you know a good function?
The only function is f of 0.
I'm going to repeat what you say because it's
The only function is f of 0 because the polynomials will have a derivative at some
okay.
point.
You say I think you're saying the same thing he says, that if all the derivatives vanish, then the function is 0. Anybody else have a? This is a democracy. Let's vote on this. So, two guys say. Well, the answer is no. So, does anybody know a good example?
That was something like e to the minus x squared, something like that.
That's good. So, this function, it looks, for example, my favorite function, and I'm going to use this function a lot, but I'm going to graph what it should. Here's 0. I'm going to graph the function. It's 0 here, so you guys are right. Only half right. 0 here. And you see the order of contact here is infinite, and I'm going to make it go up here. That's what you have in mind, is something like this. So I'm only looking at this thing locally. Actually, I'm going to make a function later on that goes up here to the height 1, and then goes back down. You believe something like this exists, certainly because I drew it with a chalk. It exists as proof, but it exists to infinity. And let's write down. It's not quite what you said, but let me write down what this function should look like here. This function could look like something like this. Okay, 1 over x squared. I made it symmetric for fun. Minus x and plus x, it looks the same, right? So 1 over x squared blows up, right? So minus 1 over x squared goes to minus infinity. E to the minus x squared goes to 0, but it goes to 0 very, very fast, right? Because it goes exponentially to 0. Okay? Okay? You can check. All of the derivatives vanish at 0. It is C infinity. You have to check it. It's not, maybe not so clear. It is C infinity, and all derivatives vanish at 0. So if I went on with this, so fk of 0 equals 0 for all k, then I don't know what to say. Because there's this stuff here, I like it because I love to construct such functions like this. I even will always call this function key. This is key for a cutoff function. I'm going to tell you why later on. But just keep in mind I'm going to use this function. Oh, why not talk about it now? Okay? You were new in this. You were not here last time, right? See? See, I watched the play. If I take another function here, say, I don't care, h, and I hit it with key, okay, what happens then? What happens to this new function here in the middle? What is it? That height is 1. Nothing happened, right? It's still h. You understand my question? It's still h. I don't know what happens here. It does something terrible. What happens out here? Okay. Is everybody following me?
What is h?
Any function. any smooth function. Well, that's a very good. Abdul has a great idea. Let's see here. Let's put this is 0, and this is 1. Okay. Okay, and now let me draw h. I'm going to have a great deal of fun drawing h. Here's 0, and here's 1, and here's, let's say h is a beautiful function in here someplace. Gauss. You like it because it's Gauss. Now, in the tail of this Gauss distribution, let us say things go bananas. It's possible, right? Okay. This is h, and this is chi. What does h times chi look like? This is the middle, I don't change it. At the end, I changed it by making it 0, right? You just agree with me. I just cut this function off, I call it a cutoff function, right? To isolate the interesting part in the middle, I haven't changed it at all, and cut off the junk on the end. You can see it's a very valuable function. Therefore, I call it a cutoff function. You hit a function which on the boundary is very bad, possibly. And this happens in the world, right? On the boundary, terrible things happen. You hit it with something that doesn't change anything in the middle, and you can push this middle almost all the way here. You could make it almost all the way here like this, right? You could do that. So no matter how far you want to push it out, not to cut it off, then you cut it off at the end and it's gone. You got it? Yeah? It's a wonderful function. It is C infinity. All its derivatives vanish at the boundary.
But I have a question. Why do we define such chi? For example, why not just define the chi which is 1 from 0 to 1 and 0 from...
Great. Great. They're good questions, and I'm going to repeat because I noticed in the videos the questions don't come through. So for example, he had many good questions last time, and sometimes they didn't have. His question was, why do you bother with this smooth stuff?
Yeah.
Just make it 1 here, and then 0 here. That's what you're saying, right? You hit h with it. What is the result? It's h here and 0 here. You took a smooth function, in principle, and made it discontinuous. Yeah? You want to stay smooth, right? You want to stay smooth if possible. So, okay? So we use these cutoff functions all the time. I will always call them chi, and they will always look like this. And you can write them down, and that was Philip's remark, you can write them down basically using functions of this type. Okay, so it is somehow related to Gaussian, it's just upside down Gaussian. Okay, so that was a little detour. Okay, so quite frankly, if all the derivatives are zero, I don't know what happens. There are great specialists who analyze various classes of functions where all the derivatives are zero. Okay? It depends how fast the function dies out. It depends on the order of contact there at zero. You can see very high order contact or low order contact or and so on. Okay. So let's just take the case, suppose for example, f is 0, f prime of 0 is 0, a whole bunch of derivatives are 0, f, the nth derivative of 0 is 0, yeah? But let's suppose that stops someplace. The n plus 1 derivative of 0 is not 0. Okay? Okay, let's look at that case. That's an interesting case, right? So that's a low order contact. You see that's just an nth order contact at 0. Right? That's an algebraic contact at 0. And that's what you guys were talking about with polynomials and algebraic feeling, right? That's an algebraic contact at 0. Okay, so that says that f is equal to x to the n times some function f, and fn, and fn of 0 is not equal to 0. Right? I just apply my process n times. Right? And then I stop because the derivative will not be 0. Alright. So fn of 0 not 0 means that fn is the nth root of a function. Well, that scares the daylights out of me because now maybe that function was negative, and I don't mind that because I'm a complex analyst, so square root of -1 doesn't worry me too much. So I know you worry about the square root of -1? You don't worry about the square root of -1. But let's worry about it a little bit here. Okay? So I'm either going to change it to plus minus and make sure that that thing's positive, so I'm not scared about square root of -1. Okay? So I have a positive function near 0. This is, of course, near 0. I can take the nth root. Can somebody here define the nth root for me? These are things that you really have to have. Really, this is not some game. You really have to have these things. I have students and they say, well, you can look it up in that book and it says what it is. You have to have it really here. Yeah? What's the nth root of something? How would you define the nth root? Do you have any feeling?
You mean on the complex plane?
No, nothing with the complex. I made sure everything's real here. I remember my 8th grade teacher said, the square root of a number is that number, so the number squared. The cube root of the, okay, this is n. But maybe for some number alpha, you can define the alpha root of that number, provided it's positive or something. Okay? What's your idea?
I would define it as a root of a polynomial.
What?
I would define it as a root of a polynomial if it's integer.
He wants to, this guy's an algebraist, I think. He always goes to polynomials. There's one and only one reason in elementary mathematics to introduce the exponential function and the logarithm. In elementary real mathematics, I mean real in the sense of real analysis. Look, I learned this in the 8th grade, so you fast track guys ought to know it now. You have the exponential function. By the way, I didn't learn e to the x in the 8th grade, I learned 10 to the x. Right? And when I was a kid, we had tables of the exponent, 10 to the, And the exponential function, as you see, is monotone increasing. It's monotone increasing, strictly monotone increasing. Do you agree? Its derivative is positive everywhere, right? It's strictly monotone increasing. Right? That means if you take a value here, a, here's the function value here, let's call this function f. This is f of a. This is the picture I learned in the 8th grade in the United States where the education is so bad. And here's f of b. There's f of a and f of b. And you notice since a is not equal to b, f of a is not equal to f of b. Because b is bigger than a, and therefore f of a is bigger than, f of b is bigger than f of a. That's the word monotone, strictly monotone increasing, right? That means that the inverse function from here is defined. This was the picture I had in my head in the 8th grade in the United States in the Midwest town of Muncie, Indiana. Okay? From Mrs. Freeman. Or Miss Freeman. We all called our teachers Miss. We didn't know. She was great. I liked her a lot. She said, yeah, I'm serious. She was terrific. And she said, the logarithm is the thing you get when you do it in reverse. That's called the inverse mapping of the exponential mapping, the logarithm. Right? This inverse mapping is smooth. How do you check it? Its derivative is 1 over x. That is smooth, okay? Because x is 1 over y, because you should think y is never 0, right? I mean, right? Positive. You got it? I'm so happy you all got it. So, now what is x to the alpha? Since I've done all this drama here.
It's e to the x of logarithm of alpha.
Right? And that is defined for all alpha. Provided, of course, logarithms exist. So provided x is positive. And then you get scared and you say if x is not positive, that was your idea. You better introduce complex numbers and worry about it also. Okay? This is really, I'm making jokes here, but this is really fundamental mathematics, right? That you have the exponential function, you have the logarithm, therefore you have powers. This is the thing you want to get. Okay. So you have this power, this is smooth, u is smooth near 0. Aha! U of 0 is not 0. Right? I mean, obviously, if you take a root of a thing not 0, it's not 0. All right. Let's continue on. F is equal to x to the n, u to the n. Oh, super, I'm incredibly happy. That's equal to x times u to the n. Right? Because I took the nth root of... Okay? Okay. Well, when I was in college, so I'm graduating now. Yeah. Okay? I took the nth root of this nth function, and then, since I took, that's u. Oh, did I write it wrong?
It's used for the van of fn.
I wrote it the absolutely wrong way. Yes. So, now chastise me. I can't write anything. Right? Sorry. Thank you very much. It's obvious what I want to do. I want to, right? Yeah, I'm terribly sorry, thank you for watching. Yeah? So I want to take the end root and put it in there, yeah? Okay? When I was in college, I remember my professor said, well, that's just W to the n. Well, my professor, and then I asked him what is W, and he said, this is W. And I says, come on, that's just some chalk on the blackboard. He says, no, W as a function of x is x times u of x. Then he said, W is a new coordinate. Right? I introduce a new coordinate. I can write that down. That's a function. And a function in a one-dimensional case of coordinate. Now, what do I need to check? I need to check that this coordinate is really smooth. Right? At least locally. This is all only locally near zero. I mean, phenomena far away, I don't know. I need to check that W is smooth. This change of variables is smooth. Okay? So I must check that the change of variables, so a coordinate change, is smooth. That was my first remark here. Coordinates must be smoothly compatible. So we had the linear coordinate x, and this new thing I'm claiming is a coordinate. It better be smoothly compatible, at least near zero. I.e., I must show that x goes to w to an x is a diffeomorphism, so it's smooth and invertible. Anna talked about, you used that word last time, I think, right? It's smooth and invertible, right? Both it and its inverse are smooth. Near zero. All of this drama with log and e to the x is applicable here. What is the derivative of this function at zero? You guys are fast. What is the derivative? Come on.
It's u prime of 0.
I'll even write it down, so come on. Don't. Great. I use the word guys as a generality, but of course the girl gets it right. What's u of 0? What's it look like someplace here? My stupid, okay, I finally got the square root or the nth root on the root. So u of 0 is positive, right? All right. What's this function look like? What's this function look like near 0? Take your hand and draw it for me. Somebody. I mean, don't come up here, just draw it in the air. For me. What does this function look like at near 0? Great. In words, now she drew the nice picture with her finger. She drew it like this. What do you say in words?
Increasing.
Strictly monotone increasing. So this function is here something like that. maybe catastrophic here, I don't care, because I'm discussing near zero. Please learn to be rough and isolate the critical aspects of a problem. How does this function look more or less at zero? Every professional mathematician can do that like that. Okay? Every professional physicist can do it like that, even better. Okay? Okay. A strictly monotone function as a mapping is invertible. We just talked about it. That means U is a diffeomorphism. That means, W is a diffeomorphism. That means I changed coordinates and found out that the function that I had was nothing more than W to the n. Or plus minus. I'm sorry, probably here there's a plus minus. And that's the difference, because you wrote like this or like this. It depends on how it's going to look. Now, at least in German high schools, and almost certainly in your high school, you spent huge amount of time talking about how functions look, extreme values of function. If the first derivative vanishes, the second doesn't, and it's negative, then you have a minimum or maximum or something like that. There is only one theorem in the entire subject. If some derivative doesn't vanish, then the function looks like plus minus W to the n. Punct. Punct. That's it. You should never use the linear coordinate in a nonlinear situation, right? I mean, why should you stupid? I mean, come on, if it's a nonlinear situation, yeah, you should use the appropriate coordinate. That means you should use the fact that the interval is a manifold, right? A manifold allows you to use any coordinates you want that are smooth. If you're doing nonlinear mathematics, you should use the good coordinate to understand better. You write some catastrophic function down like this, you have no understanding. You write this function down, every child understands it. Right? That's example 1. Example 2. You've done this also quite often in physics, but maybe not thought as you've done. The manifold is R2 minus 0. It quite often happens in physics that you have a base point where you have a potential of something blowing up. I mean, there's always some point where something catastrophic happens, maybe. You have to remove it from the consideration, right? Now you have standard coordinates here. So let me say standard coordinates. Well, let's make a circle here so we remind ourselves. I love to use color chalk even for myself. It's, when I'm making my own calculations. It helps me immensely. I really like it. This thing's no longer there. And we have standard coordinates. So we have standard linear coordinates. X, Y. So if you have a point here, P, then you have some projection here, and you get this length here is X, and you have some projection here, and you get this height Y, right? And those are the assume in life that you don't understand anything, and always start before breakfast, really, telling yourself how stupid you are, and let me see if I understand coordinates. And take some example like this. I did this before breakfast and realized, I like it. I had some fun before breakfast. Then I had muesli, and then some bread. It's very nice. I felt better. And I realized of course, I know that there's something, I call it P maybe, for polar coordinates. And this is a mapping to R plus times S1. Well, you know what I'm talking about, right? So let me write it xy, so I'm writing the change of coordinates. Right? I'm writing the change of coordinates in some sense. xy goes to, well, this is going to be really, let me write it the way my 9th grade teacher, no, this was my 11th grade teacher wrote it. R theta. There's some major question, what is an angle? Do you realize? It's not at all clear what is an angle. You understand what I mean by polar coordinates, right? Sure. I hope. At least the letters you've seen before. R is then the square root of x squared plus y squared. And I complained to somebody that you should never use R, you should always use R squared. I was complaining to you. But here we remove zeros, and this is okay. This is a smooth function. This is C infinity function. So at least that part of it is C infinity, right? That's okay. Right? That coordinate is okay. That's smooth. Okay. Well, here's S1. Sphere of radius 1. So an angle, I don't know, here's the point 1. An angle is a point here, theta, or maybe theta. I don't know what these letters mean. You should sit down and think whether you really understand the notion of an angle or not. I've thought about this for myself for a very long time, even after breakfast. I'm serious. Okay, that's theta. Well, theta has the other coordinates xy. All right, that's the other coordinates. Okay, now I'm going to make 4 charts on S1. And you see my 4 charts? Here's one. Oh, we got the color chalk thanks to Latif. So we have, this is a region. Let's call this U1. And the coordinate I'm going to use on U1 is y. So this is xy goes to y. Okay? You agree, at least pictorially, I mean it's completely clear what I'm talking about. That is at least parameterizes this part of the circle, right? This height parameterizes this part of the circle. If I would have gone here, this height would not have parameterized, right? It would have been stupid. So I am not stupid. I try not to be stupid. I take this part, this will be U2. Now, I'm only going to talk about these 2 coordinate charts, but I mean, there will be 4, you can see it. This, and this, right? Okay, so here, obviously, I'm going to do the same thing. I'm going to use x. Okay. Okay. This is U1, and this other thing I'm going to call U2. Okay. And okay, let's have some fun now. Here we go. V1, that's the interval in the y-axis between -1 and 1. That's V1, this is V1 here. Now I go backwards to, I'm going to go backwards to U1, and the mapping I'm going to have here is given by the well-known equation of the circle, right? I had to go back to the circle. So I start with y, I know what I have to get here. By the way, I hope I've got this right. Yeah, you see I've got a plus sign here because I'm really in this region here. That is in U1, okay? And now I regard this as being in U1, 2, but I regard it, that's the intersection of U1 and U2, so I regard it as being U2. And then I take it down to V2, and that means I go to X, so that means I go to 1 minus, you get it? I have in one coordinate patch, I have in another coordinate patch. The change of coordinates is going on. Where is the change of coordinates? The change of coordinates is going on in this region here where I have to watch out. This is U1, U2. Right? That's where I change coordinates. Okay? Well, I don't need to discuss the matter. This function here is obviously smooth, invertible, everything you want. Okay? Yeah?
How can you define it? I mean, the function doesn't go from -1, 1 to U1, 2.
No, of course not. I didn't say that this mapping was subjective, so,
No, but -1, 1.
okay,
If
so
you take
I
the
left
mapping
out,
from there, it's,
no, okay,
it's
no.
not correctly.
I put this in, let me for you, you're an algebraist by heart, let's see here. I go but I like to put, I was sloppy here and he didn't like it. So I go here to U1. Okay? And now in U1, I have U1, 2. And now I regard this in U2. And once I have U2, I can go to V2. So I left this step out here thinking it was obvious, but it's obviously not, so thank you very much. Okay? You see what I did? What he's saying is I can't go from here to here without going to the intersection. That's what you're saying, right? It's obviously right. Okay? So it goes, can you read that? This is just the coordinate, inverse coordinate map, phi1 inverse. Here's the inclusion into this intersection. Here we go down to phi2. So this is phi1 inverse phi2. Change. So you need 4 of those charts to do that. And I'm telling you, that is exact what's going on with polar coordinates. Now, in my childhood, I wrote x equals r cosine theta, y equals r sine theta. And my teacher said, invert the map. And I said, okay, r equals square root of x squared plus y squared. Right? And theta is arctangent. I knew these words in my childhood. I forgot them in my adult life. That is the algebraic manipulation that you can do here before breakfast. Yes, you can even do it in your head. And you can do it fast and stick in some equation and get some answer. And it's probably going to work because it's justified by what's going on back there. Okay? Those are 2 very nice examples I recommend that you look at. Okay. Now, going through the last lecture of Anna, we talked what are tangent space. Well, you have a manifold. And again in the 8th grade, in physics, of course. Probably in physics we had some, some force vector or something, I don't know what, something that I couldn't understand because it was physics. Right. Velocity vector. Gravity. Gravity is good because it's straight down. No, shoot a gun, right? You have a gun, you shoot a cannon. That was their origin. That's the reason the Prussian army loved mathematics. There were 2 reasons. The Prussian army loved mathematics because you have a cannon, you shoot it, and it lands here and so on. Right? Another reason they liked it, mathematics, is they realized that if you walk over a bridge in formation, do you know this? If you walk over a bridge, the Prussian army is not like the Romanian army, it's completely chaotic. Or Nepal, is there an army in Nepal? I don't think so. Probably there are many bridges in Mount Everest, but there's little tiny bridges with 8,000 meters straight down. But you walk across a bridge in formation, and there's something called resonance. And have you seen this unbelievable film of what happened to a bridge in the state of Oregon? You can find it on YouTube, I'm certain. Somebody happened to film when that happened. Some wind came, and it completely destroyed the bridge. I mean, it just blew it up because of this resonance. And mathematicians figured this out and told the Prussian military about this, and the Prussian military really liked it. So nowadays there are other things to discuss. Yeah, physicists do this, things physics invent. So mathematicians are peaceful nowadays. Okay, so that is an arrow, and it means directional derivative in that direction. Okay? And that doesn't make any sense at all in this picture. You need something to make sense out of that. Okay? So you say, let's take a coordinate chart. That's you, and it goes down here to something here. Say to some vector in vector 0, so this point is P0 maybe, and it goes down to a vector V0 in Rn. This is V. Now you're in Rn. And as Anna told you, it's okay to write a vector here. Right? Well, what you're really doing is saying, I'm writing a vector, really a pair. I'm writing a pair, a vector, and let's call this thing alpha. I'm writing a pair, namely, in German we say Fußpunkt, so a point at the foot of the vector, and the vector. Right? You have to somehow say where the vector is starting. Right? So how are you going to think about this if you're in Rn? Here's 0. Here's the vector. Okay, I'm not doing very well. And here's the vector. Okay? And then you consider the affine line defined by this situation. You consider the affine line defined by this situation. It is affine. The word affine means you don't have any base point, any 0. You don't know whether you should consider the affine line. It doesn't go through 0. It's not a vector subspace. You consider this affine line. An element of this affine line is V0 plus T. Oh, this is a very bad. It's good for a line, but not good for. So it's V0 plus T times alpha. Right? Okay? As soon as you have a vector, that's your Fußpunkt. I don't know foot point in English, but I like Fußpunkt in German much better. That's your Fußpunkt. And then you have the vector going there. That's what it is, right? Okay? And what Anna told you about, I'm sure, is you differentiate a function along that affine line at the Fußpunkt. Isn't that the way to differentiate something in a directional derivative? I hope you do it that way. That's the most efficient way to do things. Right? You have a curve. You have a curve here that happens to be just an affine curve. This is the directional derivative of f in the direction alpha at the base point v0. Okay. Then Anna told you, well, if you have general coordinates, so x a coordinate, this is the coordinate mapping. X is the mapping that goes from u to v. Then, in fact, these directional derivatives, what is the direction here? Where did it go? Alpha at of f at v0 is just some alpha I partial derivative xi and x equal v0 applied to the function f. Of course, I'm writing the function in the coordinate. That's all you do. When you learned calculus, you had angles in there, remember? Those are the angles of the vector. Cosine, some cosines and all this stuff, that's nonsense. That's because you have a unit vector, right? This vector is not a unit vector, alpha. It's just some vector. Okay? Okay. Every derivation is linear over the real numbers and satisfies this equation. I'm going to get d of g. Sorry. D of f. So the two equations, Anna told you about this. It's R linear. And it satisfies this rule, which you call Leibniz rule. Right? Leibniz rule. Gustav's happy because he likes Leibniz algebra. Leibniz was a German mathematician of the 17th century, almost at the time of Newton. This is the Leibniz rule. Leibniz rule tells you how the derivation works with respect to multiplication. The smooth functions, I'm now going to talk mathematics. Excuse me, you need to learn some mathematics. The smooth functions, you can add two smooth functions, you can multiple linear combinations, that means it's a vector space, smooth functions, right? You can do all that stuff. But what you can do there is multiply two functions, right? That's an additional algebraic structure. So the operations on this algebraic structure, you always ask how they respect this operation. And the first thing you ask is how does something like a derivation respect the algebraic structure, and that's the rule. Okay. It's called Leibniz rule. And you see you're evaluating at the point P. So what it says is that every a derivation is always of the form some AI partial derivative xi evaluated at the point of question. And you see that that means those are all of the derivations of these functions. You can always write them like this. And that implies that the tangent space was the space of all these derivations. I'm repeating Anna's lecture, but you should have these things in your head. This is an n-dimensional vector space. You see, you have the n partial derivatives, and you have complete freedom for the direction. You see, in my direction here that was called alpha, I think, this is the freedom in the direction. But without the coordinates, I don't know how to write it down. Okay? So abstractly, it's just a derivation. Okay? But as soon as you give me coordinates, I can write it down. Okay? So after this long review, comes something new. So in the last 12 minutes of the lecture today, the new considerations. You've heard the word field in physics. Field theory is a big name in physics. So we're going to discuss what are called vector fields. Now, you should think, look, you should think at all levels. You should think, first of all, at the level of a child. And then more sophisticated, more sophisticated, more sophisticated, more sophisticated. Okay? Try your best to be more sophisticated. So smoothly varying tangent vectors. Well, it makes sense because if you're a farmer and you have a manifold, I used to live in the country and love very much talking to the farmers out in the country and about their manifolds. And in their manifolds, at each point, I mean, a farmer's got to understand that. I mean, he has a piece of wheat or something, and it's oriented in some, I mean, you see this physically, right? You see some force field, perhaps. I think force is a field. You have to be very careful with concepts here, whether they're really fields or dual objects to fields, which are called one forms. So I use the word, if I say force field, I use it loosely because it may be a one form. And I'll talk about that later. But let's just talk about this as an arrow. Okay? So it's oriented to some length at each point. Well, and it varies smoothly. So no particular jumps, just very smoothly, very, okay. So that's what you tell your mother when you go home, that you've been studying vector fields and they're smoothly varying tangent vectors. That is not useful. What a vector field is, and I will write it with a big letter here, means X is a mapping from C infinity to C infinity, which is a derivation. That means it's a linear mapping. And it satisfies Leibniz rule. Okay, here we go. I told you. There are operations on a vector space. You can add, you multiply by scalars, and you can multiply two functions. Right? Here, you're going to take a derivative and get a derivative of a function, and you're going to get a function. Do you understand here what Anna was doing in the last lecture? She was taking the, where the heck are we? We're taking the derivative, we're taking a function, taking its derivative at a point, and getting a number. Right? Here, a derivation takes a function and gets a number. Right? Here, a derivation takes a function and gets a function. That means you just don't evaluate at the point. You get the answer all over the place. That means you differentiate it here in one way, differentiate it here in another way, differentiate it here in another way, differentiate it here. It doesn't matter. You get a field of derivatives. Okay? You get a differential operator, which is a first order linear differential operator, we call it. Well, it satisfies Leibniz rule. And of course, is what you expect. F times x of g plus g times x of f. But these things are not numbers anymore. These are functions. You see here, this is not f at the point P. This is just a function. Okay? Okay? Well, let's conclude this lecture with some fun. One of the fundamental questions in mathematics, physics, is if you have a vector field given, can you find curves? Can you find curves so that the vector field is tangent to the curves all over the place? Here, at a point, we were able to find a curve that was just one vector. That wasn't very hard, right? We just found this curve. It was v plus t alpha, right? That was just at one point we got it. Here, the question is, can you find curves which are tangent to the vector field all over the point, at every point? This question is the fundamental question first question of ordinary differential equation. And I'm going to explain that. Yeah.
I have a question. How do you define like the vector field on a manifold? I don't get it. How do you assign at each point a vector?
Very good. Very good. Let's answer his question and not go on to the let's just concentrate on his question and we'll finish for the day, okay? Let me repeat your question. Let's see. Say it again. There are two things going on here. One is a tangent vector at a point, and another thing is my picture here, so to speak. And I claimed my picture somehow is a field of tangent vectors. Yeah? And you're saying, how do you get that? Is that what you're saying? Okay. Let EP be the evaluation mapping. It's a very good question. Don't be afraid to write formal things down. That's what he's asking for. And sometimes if you don't have a clean understanding of formal things, it'll mess you up. Yeah? He's saying, let EP be the standard, be the canonical evaluation map. Say P in any P in F. Namely, EP, E for evaluation of F, is F of P. I'm sorry, that's so formal it's even boring. I just evaluate a function at a point. Okay? By the way, Dirac made a big business out of this. Dirac says, you've heard of the Dirac measure. Integral of a function against the Dirac measure is the evaluation of the point. So this point evaluation thing, yeah, you have a function, you evaluate at a point. That's a very important operation, to evaluate a function. It sounds completely ridiculous, right? Evaluate a function at a point. But it answers this question, right? Because now I have a new tangent vector. So tangent vector at P is evaluation at P of the vector field. So you differentiate a function all over, and then you evaluate the result of the point. Okay? you check that this tangent vector, this is really a tangent vector.
So you get a lot of vector fields.
Yeah,
for every.
a lot of tangent vectors. You said a lot.
Well, no, a lot of different vector fields for each x.
But why don't you tell them about the tangent boundary?
No. No. You give me a vector field, one vector field, okay? I say, for every p, I get a tangent vector from that. How do I get it? Well, I just compose the vector field with the evaluation function. Maybe if if I draw a picture, maybe it'll help. It helps me sometimes to draw a picture. This mapping here, you differentiate the function and then you evaluate it. It's a tangent vector, but you evaluate it at p. So to answer your question, I have to evaluate it at each p. Right? Does that help?
No, it just has to be x is fixed.
X is fixed.
So for each x, I get another vector field. That's what I'm saying.
No, I don't see the other vector field. What do you say?
But if I change x,
What a big X.
yeah, the big x. If I change x, big x.
No, you get another vector field.
Then that's what I'm saying.
Well, that's completely obvious. If you exchange one vector field for another, you get another vector field. But I think you're thinking something else. I mean, you take another vector field, you get another. Maybe let me draw a picture. I don't know. I mean, this is.
So the thing you did on the blackboard is just definition.
Yes. A vector field. Oh, perhaps maybe I made a sloppy. I'm saying definition and notation. So I'm sure this my sloppiness is confusion. So definition of the space of vector fields is vec m, and I'm defining an element to be a vector field or in vec m to be this. Does that help? I think.
But here you wrote the derivation. Does here this derivation really mean something, or is it just some notation? It's not derivation knowing the R space.
What do you mean it means something?
For example, I can suggest, for example, I remove this derivation. I say this function which maps from the smooth function of m to smooth map of m, and it satisfies these two situations. Then we can say it's a vector.
It's a vector field, yes. Yeah.
So this is derivation.
Okay, here's the definition. Is because I hurried too much here, and I think I confused some of you again to make sure. This is the notation. I'm saying something is a vector field if it's a derivation on the full algebra, not just evaluating out, right? And that means, I just wrote it again what it means. I think that's a confusing thing for you. These two conditions. And the difference between a vector field and a tangent vector is I'm not evaluating here. But if I do evaluate, I think that was what you might have asked, I'm not sure. I get a tangent vector, and I get it at each evaluation, I get a tangent vector. So in that sense, is a smoothly varying field a tangent vector? Okay? Now, to close this topic here, locally, and I'll start here tomorrow, x, so in local coordinates, x is equal to some ai ddxi. And now look here. These are the basic, in coordinates, these are basic derivations. I haven't evaluated here. So you apply these to a function, you get a function. And these things, so this is the basic derivations in coordinates, and these things here are functions. So these things are C infinity functions. So the difference between this blackboard here and this blackboard there is here everything is moving. Right? Every p you're doing something here. And that means you're differentiating at every p and getting a function. The coefficient is moving here. You see it moving. You see, right? You see it moving. Well, we're going to do many examples tomorrow, so I think that's enough for today, but that's the difference. Either at a point or moving. Okay? Thanks.
Here, AI is just a number.
It's a number.
tak,
Yeah, I'm not sure what the AIs are.